Last time I explained to you that for any Lie group, the tangent space at E, so G is a Lie group, and then TEG acquires a structure of a Lie algebra, which means that this space has a binary bilinear operation commutator which satisfies two unusual conditions. One is anti-commutativity, that is, so the commutator this is the notation for it. And now the axioms are the properties, anti-commutativity, and Jacobi identity. This is how it looks like. Zeta. No. Eta zeta xi, yes. Xi eta is 0. There are definitions of this operation, and one of them is very simple. Just we take an element in TG as a whole is the same as the set of all Sadleyev invariant vector fields on G, and we apply usual commutator operation to vector fields, and we get this operation. Another description, which I'm going to use now, is more geometric. I will not give the definition because I'm going to use it, and you immediately will see what this definition is. So, example. I say GLN R for GLN C will be absolutely the same. In many respects, this is the most important example, because immediately we have what I'm going to say about this Lie group will be immediately true for subgroups. So, G is this. Suppose that I do not prefer to use these notations, because actually A and B are matrices. This is the same as the set, the space of all n cross n matrices, absolutely all, degenerate, non-degenerate. And now I want to find the commutator according to my definition, to the definition which I'm going to use now, and I suggested it last time. The best thing is to do the following. We consider four elements of the Lie group. Then we take the commutator of this and this, which means this time, this time, this time, this. And actually, it is going to be I plus t squared times something. I mean the series, full series. And this something will be the commutator of A and B. So we do what? This is I plus TA plus t squared a squared over 2. So on, which I don't actually need. This is I, the same. This is I minus TA plus, however, t squared a squared over 2. And this is I minus TB, everything Okay? Now I want to compute, again, up to the term t squared, the expression e to the power ta, e to the power tb, e to the power negative ta, e to the power negative tb. The term of degree 0 is just I, right? I times I times I times I. Plus t times what? I need to take one term of degree 1 from one of these four factors, right? And I elsewhere. So this will be t a plus b minus a minus b, which is very much 0. I do some computations, and you ask if you need any explanation. Now, plus t squared times what? First, we can take each of those times I. So I write this a squared over 2 plus b squared over 2 plus a squared over 2 plus b squared over 2. And also, we can take double products of two terms of degree 1, right? There will be 6 of them. This times this plus ab. This times this minus a squared. Then this times this minus ab. Next, these two minus ba. Then these two minus b squared. And the last, these two plus ab. I do not need terms of degree 3 or more. And as to this, certainly it is equal to ab minus ba. And I hope you will agree that there are some consolations which lead to this. Is it okay? Okay. So, the result. The commutator in the algebra of the group G, L, and R, which is as a vector space, the space of all matrices n cross n. If this, the commutator of A and B, is what it certainly should be, AB minus BA. This is according to my description of the commutator. Is it okay, or you have questions? If you don't have questions, then let me say, I said this last time, it is sort of obvious that a homomorphism between Lie homomorphism is different, is a Lie algebra homomorphism, that is, it respects commutators. In particular, if we have a subgroup of a Lie group, then the corresponding Lie algebra is a subalgebra of the Lie algebra of this Lie group, right? To say that GL and R has many subgroups is to say nothing. As I said to you, actually almost any Lie group is isomorphic to a subgroup of some group GL and R, or GL and C in the complex case. And locally it is not all the same is true without any almost. So it is very important to consider subgroup of the group GL and R and the corresponding, well, the corresponding Lie algebras, because of the same commutator, A minus B. The Lie algebras will be subalgebras of this Lie algebra. So I consider two, S, L, and R. Very much algebraic elementary algebraic question. Can you imagine a matrix A says that the determinant of the exponential is 1. Do you know what? For which matrices the exponential has the determinant 1? You should not all know this, mostly because I said this to you. Trace 0. This is certainly a very, very interesting fact. How to prove it? There are 1,000,001 proofs. For example, what happens to the eigenvalues when you take the exponential? They also, so if lambda 1, lambda n are eigenvalues of A, then e to the power lambda 1, e to the power lambda n are eigenvalues for exponential A, and this is absolutely obvious. Let's take the same eigenvectors. The same eigenvectors. Determinant, well, e to the power A is determinant. Nobody has cancelled the fact that the determinant of a matrix is the product of its eigenvalues. The product of e to the power lambda 1, so on e to the power lambda n, is, as some people know, e to the power lambda 1 plus 1 plus lambda n. That is, e to the trace, the determinant of e to the A is always equal to e to the power trace A. It is 1 if trace A is 0. Who can have any objection to this? Yes, so this is the fact. This is the fact. So SL and R, the algebra, consists of all matrices with trace equal to 0. So in particular, I state that if you take a commutator of two matrices with 0 trace, then it will be again a matrix with 0 trace. But actually, one much more is true. The commutator of any two matrices has 0 trace, whether they have trace 0 or not. Because trace AB is equal to trace BA. And hence, trace AB minus B is equal to 0. So this is true. Now, ON or SON, SON is connected, maybe more convenient, but it's all the same. The corresponding Lie algebra is what? It is again some subspace, some reasonable subspace of the space of all matrices. And this is the space of, it is the space of skew-symmetric matrices. The space of skew-symmetric matrices. Well, I can leave this to you. It's very easy to understand. It's actually much more easy than in the case of SLN. And in particular, the commutator of two skew-symmetric matrices, it is less obvious, but still true. The commutator of two skew-symmetric matrices is skew-symmetric. What about the commutator of two symmetric matrices? Is it symmetric? It is also skew-symmetric. So symmetric matrices do not form a Lie subalgebra of the Lie algebra of all matrices. The complex case is more or less the same. There are two interesting groups, unitary group UN or SUN in a different group. Also O and R are orthogonal, O and C, orthogonal complex matrices. And the corresponding Lie algebras are correspondingly the Lie algebras skew-Hermitian matrices. You understand? Skew-Hermitian, the transponent is equal to minus conjugated. minus a bar, because the transponent of AT is minus a bar. And this is for UN. For SUN, additionally, you need to require that the trace is 0. And U, and what? Yes. Oh, and C, the Lie algebra is the Lie algebra of all symmetric matrices in the same sense as the real case. AT is negative A. So this is a description of the most important Lie algebras of Lie groups. There are other Lie groups, they also have Lie algebras. Now my main idea is to explain that this correspondence between Lie groups and Lie algebras in many respects is very rigid. More or less, every fact about Lie groups can be translated as a fact about Lie algebras and vice versa. So actually, in many respects, the study of Lie groups is equivalent to studying Lie algebras, which is more algebraic, and by this reason, in many cases, provides less difficulties. Certainly I need to mention, because this is my subject, that it is so in the infinite case. This rigid correspondence between Lie algebras and Lie groups is very much finite dimensional. I will not say anything more, anything else about this, but if you are interested, you can find this in corresponding literature. So, when I say that the correspondence between Lie groups and Lie algebras is very rigid, I mean the following theorem. Something which we already know, that if F is a Lie, maybe better to write H into G, because at some moment H will be a subgroup of G, which is more natural. A Lie homomorphism. Then certainly there arises its differential df between the Lie algebras. The usual differential respects commutators. This I explained to you. And now, so df certainly is reconstructed from F. How much this correspondence is one-to-one? That's the following theorem. The first part, much easier than the second part. If you have two homomorphisms, and then I say, certainly for this purpose, I need to assume that H is connected. Then F is equal to G. So a homomorphism between Lie algebras is determined completely by the corresponding by its differential. I can say about this that in some sense it should be so. It's convenient to make a slightly different formal proof, but from the point of view of intuition of ideas, it should be so, because elements of Lie algebras correspond to one-parameter subgroups. Any homomorphism between Lie groups takes one-parameter subgroups into one-parameter subgroups. So if they have two homomorphisms, if they coincide, if the differential coincide, then they coincide in every one-parameter subgroups, which means a lot. At least in some neighborhood of the identity, everything is covered by one parameter subgroups. I will say, well, let me first formulate part B. And then I will give a proof of both. A is several words. B is more involved. That is, if I have two Lie groups, and they have some homomorphism, phi, then my problem is I want to construct a Lie homomorphism f h into g such that the f is phi. So my previous statement A means that this correspondence between Lie homomorphism and the algebra homomorphism is one-to-one. Now I want to say that it is onto. Not that it is completely true, but at least it is what I need. So to make it true, I need to say one of two things. And your choice. Actually, it's better to understand both. H is connected. This I always assume. Now, well, G also can be regarded as can be made connected because any homomorphism, a connected Lie group, its image will be within the component of identity in G. So G also can be assumed connected. It is not harmful. Now, one or two things. I say three things. First right statement. There exists a local homomorphism with df is equal to phi. This is always true. What is the local homomorphism? It is a map of some neighborhood of the identity element in H into G, which is as much homomorphism as it can be. So a local homomorphism. A local homomorphism. It is a map of U, where U is a neighborhood of E in H into G, such that if H1, H2, and H1, H2 all belong to U, then f of H1, H2 is equal to f of H1 times f of H2. And also, if H and H inverse both belong to U, then f of H is equal to f of H inverse. This is a description of a local homomorphism. Do you understand? And certainly local homomorphism, precisely as global homomorphisms, induce homomorphism of Lie algebras, of the tangent spaces. Differential is very much local. We do not need to know the map far from the point, right? So local homomorphisms induce homomorphisms of Lie algebras precisely in the same way as usual global homomorphisms. And then my statement, one of possible statements of part B, is that there always is a local homomorphism which gives this and this. Now, globalization. Here we need to be cautious. So this is a statement of part B, local homomorphism. Now, another statement. There exists a covering of H. This operation does not affect the Lie algebra. The projection is local diffeomorphism, so in the neighborhood of E, these two groups are the same. There is a covering and a map F H tilde into G, so that df is phi. This is the right way to globalize the statement, to make it global. Local homomorphism is local homomorphism, but if we want to make it global, we may be, it's possible that we will need to replace H by its covering. Or, if you prefer this language, you are fans of complex analysis of such things, prefer the language, I can say that there exists homomorphism H and G, but maybe multivalued. Precisely the same as in complex analysis. When you globalize a holomorphic function, you certainly extend it to a bigger and bigger domain, and at some moment you find that in the process of this extension, you return to domains, to parts where the function was already defined, but the new function is not equal to the old function. Precisely the same here. So this is the statement. For there exists a homomorphism of a covering. And the third possibility, which is a weaker possibility for this, you can imagine that H is not just connected, but H is simply connected. H is simply connected. And if we have this, then actually no coverings. Every covering of H is the same as H. So if H is simply connected, then the theorem is true in the most, well, the shortest possible statement. You have a homomorphism between two algebras, yes, and then property. If H is simply connected, then yes, there is a homomorphism of legal with this differential. And that's all. Now let's turn to the proofs. For A, it is very simple. So this is A. We have two homomorphisms. We want to prove that they are the same. The most obvious thing to do, consider the set A in H where f of H is equal to G of H. Yes, so H in H, where these two things are the same. Okay? Yes. Certainly it's not empty, because if H is either, this is very much true, without any conditions, right? We know more. We know about one-dimensional subgroups. Now, what do you think about A? Is it closed? Is it open? What's your learned opinion? Closed, certainly. Two continuous maps. Forget about homomorphism, I don't know what. Two continuous maps. The set of points where they are equal to each other is closed. So A is closed. What about openness? Not open. Open. Yes, you're optimistic. Me too. Why? You know, if you have two continuous maps, then the set where they coincide shouldn't be open in general. No reasons for that. But here we have not just a continuous map, we have homomorphisms. So actually A contains some neighborhood of E. I have already explained this. The two maps are the same on every one-parameter subgroup of H. One-parameter subgroups, even if they do not cover, the whole space, the whole group H, they cover some neighborhood. This we know. So there exists an open neighborhood, very much open neighborhood of E, where it is true. Also, actually, A should be closed with respect to multiplication, right? Two homomorphisms. So if A is contained in A, then AU is contained in A, right? A is contained in A, U is contained in A, the product is contained in A. And this means that every point which is in A is contained in A with some neighborhood. I don't know what else to say about this. A closed open subset of a connected space, the whole space, so they coincide. Now part B. Well, before the class, I discussed it with some people. Somebody could come after, so I repeat this. But now I repeat it not as a question, but rather as a statement. So there is such a word distribution. I personally know at least 3 different senses of it. So it is not a probability class. No. A different kind of distribution. A distribution, if you have a manifold, n-dimensional manifold, then a k-dimensional distribution is so if you have a manifold M, dimension n, and k is a number, then a k-dimensional distribution is the following. For every point P and M, we have a subspace distribution A, P, in the tangent space to M of dimension K. And I even don't want to write it because it can be formulated in different ways. It should depend smoothly on P, at least continuously. At very least continuously. But derivatives sometimes help. In terms of local coordinates, it's very easy to understand what actually it means. Now, this distribution is called integrable. If for every P in ML there exists a k-dimensional submanifold SP in M. It actually, for our purpose, it will be a very small submanifold. It is a submanifold of some neighborhood of P. I do not want anything global. Of some neighborhood of P. Say that for every Q in SP, TQ of SP is the AQ. So such a family of planes and an integrable surface. Integrable surface It's called the integral surface. An integral surface is such a thing, which is tangent at every point to the plane of the distribution. Then, well, I said this, some people were here, some people came later, so I repeat. If k is 1, well, I do not consider the cases k is 0 and n because they are too trivial. So if k is 1, then the fact that every distribution is integrable, that is, for every point there exists a curve which is tangent to all the lines of distribution, this is a fact from elementary course of differential equations. It has a proof, classical proof belonging to Euler. And it's important for differential equations. Actually, it is accompanied by the statement of uniqueness. Statement of uniqueness is always true. This integral surface, just one integral surface, if it exists, it is unique. It is very easy to prove. We can discuss it, but I don't want to go too deep into this subject. It is very easy. Follows immediately from the one-dimensional effect. Just take a reasonable section of everything, and you will have this uniqueness. Yes. Now existence. There is a statement which is called the Frobenius criterion. Of the gravity. I need some terminology. A vector field X. So I have a distribution A. I do not need to introduce this notation again. A vector field X is subordinated to the distribution A if for every point P again, in M, it is not for A groups. The vector of this vector field belongs to AP. You understand? So I take a vector field, which actually for every point, we take a vector from this distribution. Is it clear? Now, the criterion, maybe you can guess. A distribution is integrable if and only if. Commutator, you can call it Lie bracket. But you're right. Distribution is integrable if and only if the commutator of two vector fields subordinated to this distribution is also subordinated to this distribution. If the dimension is 1, you know, then all the vector fields are almost the same. Just some vector field times a function. Certainly, a commutator of two such vector fields will also be the same vector field times some function, right? So if k is 1, it's not a problem. If k is 2, there is a problem. If you take at random a distribution, it will not be integrable. Just for those of you who are interested in, I can even include this in my list of exercises under some number which I will determine. Suppose we have the space R3. Now what I consider, I call it a differential form, if you know what it is. Y dx minus dz. At every point, actually this is a plane. The zeros of this form present a plane, right? Yes. Sometimes it's called the standard context structure in R3. It is absolutely not integrable. Cannot be integrable. No point. If you have a point, then no tiniest piece of a pseudo-matrix surface can exist which is tangent to this distribution. So this is an example of a non-integrable distribution. Now I have 5 minutes. I have a choice. Either to use this fact to at least to begin proving theorem, or to give you some hint how to prove this theorem. If you don't know, maybe somebody knows some good reference. Because I can say what I always say in this case. I can say that every reasonable textbook in analysis should contain this. But then we discover that there are no reasonable textbooks. So I prefer not to say this. But still, probably, I don't know if you take, I don't know, Nachtigall, Hunter, technically in analysis, the applied analysis, very much applied, this criteria. Then maybe it should be there. I'm not sure. Well, let me maybe better do this. So next time I will present, if not a proof, then at least something which will convince you that this is true. And now let me show to you how it can work. So we prove a part of theorem B. Suppose that we have a Lie group G with Lie algebra G. Then we take any subspace, any Lie subgroup, any Lie, at last, Lie subalgebra, H in G. Then I claim that there exists locally a local Lie subgroup. Local, this means that actually it is defined only in some neighborhood of E. Globalization is a different question. So some submanifold in the neighborhood of E, which is a subgroup with this Lie subalgebra. This is my first claim. My second claim that it follows from the Frobenius criterion immediately. How? So this is our Lie group, as you can see. This is E. The tangent space, I will not draw it, is the same blackboard, and this is H. Now I do what? I apply to this H all differentials of left translations, right? I can write G H, it is not quite correct, so I take the differential of lambda H, apply it to H, and I get a plane there. Then I have a distribution, very much left invariant. Of dimension equal to the dimension of H, right? Is it integrable? But yes. You see why. There are, so let us fix some bases in H. Let us consider corresponding left invariant vector fields. They all are subordinated to my distribution, obviously. Moreover, if we take any linear combination with functional coefficients, this is subordinated to the distribution. Right? So this is true. Vector fields subordinated to a distribution form a vector space module over functions. You multiply them by functions, if you add them, they're still subordinated to the distribution. Moreover, this is all. at every point, the vectors from vector fields lambda eta 1 lambda eta m form a basis in the corresponding space of our distribution. So whatever vector field subordinate to our distribution which you take, it will be a linear combination of this with functional coefficients. After this, since H is a subalgebra, so a commutator, the commutator of two left invariant vector fields is again a left invariant vector field, so is a linear combination of L eta i's with actually numerical coefficients. This follows immediately that actually this is the full amount of vector fields subordinated to this set of vector fields subordinated to this distribution is closed with respect to the commutator. Then we apply the Frobenius criterion. We find a surface of dimension equal to the dimension of H, which is tangent to this distribution, and then immediately, in 2 seconds, using one-parameter subgroups, we find that this is a local subgroup of H, of G. Well, I will repeat this next time. My time is very much over now. Yes. So this is how, and actually everything follows from Frobenius criterion immediately. So we need to understand that Frobenius, need to believe somehow that Frobenius criterion is correct. It's true.